Hello and welcome. I'm Bill Wake. We're here working on a new project this week. It's an experiment in evolutionary design. We've got a basic interpreter, and it's using a recursive descent approach to parsing. So our goal is we're going to evolve that thing from using recursive descent to using Parser Combinator approach. So over the last couple of weeks, we developed a Parser Combinator library for Swift, and we want to apply that in. Now, in this case, I'd like to make that switch smoothly in little tiny bites. You know, you can't always do that, but where you can, I think it's a great way to move forward. So let's do a little background on the interpreter and on evolutionary design, and then we'll get into the code. So our core piece is we've got this basic interpreter we wrote, I don't know, a couple months back, and an interpreter is sort of like a compiler, but the interpreter does things more in a runtime way. So you feed in a program, and then the interpreter kind of looks at the program and decides what should it do at this step. It might be input or output, and it does it, and then figures out where the next step is, goes and finds that and analyzes that and does that step and kind of works its way step by step. There's never a whole implementation in some other programming language. It's all done in one language. It's not compiling it to machine code or anything like that. It's just working on it at the level of whatever language we're using, in our case, Swift. All right, now if you look inside interpreters, they look a lot like compilers. So a compiler and an interpreter, you feed in a program text, it goes through some sort of lexical analysis, also called scanning or lexing, and that gives you a stream of tokens. So token might be a variable or a plus sign or a left parenthesis or whatever. And then you feed that into syntax analysis or parsing, and it produces a tree of nodes. And usually the nodes are things like statements with other statements inside, or expressions, with plus and minus and times and so on. Once you have that tree of nodes, that's what we're actually interpreting in our case. I mean, there are interpreters that just go directly from the text and don't build up these trees. I don't know, they must build up some sort of tree-like structure or reverse Polish or something, but they may operate more directly from source. Ours builds a tree of nodes. And then the interpreter just walks through the tree, and if a node says print something, it prints it. If it says read something, it reads it. If it says calculate this value, it calculates the value and stores it somewhere, and then goes on to the next piece of the tree. Okay. Now, if it were a compiler, instead of interpretation, we'd have code generation, and it would spit out code, and that code would run the input and output, and probably run 10 times or 100 times faster. All right. So the piece we're going to focus on is that piece in the middle, the syntax analysis or parsing. And the way we did it in up till now is this, it's called recursive descent. And the idea is it's all kind of one of the big ideas of compilers from the 1960s was like, hey, if we make everything drive off the syntax of the language, things will get so much easier. And so we start with a grammar, and part of the grammar for expressions is an expression goes to a term plus a term or minus a term. So you can go term plus term plus term plus term. The braces tell you 0 or more. And, in sequence is just one following the other. And the vertical bar says this or that. So it's a term potentially followed by a plus and a term and so on. Okay. And in recursive descent, we make a translation. So we take that grammar rule and we make a systematic transition into code. And so there's sort of, well, you do it by hand, it's easy enough, but you could do it by tool as well, at any rate. And so what we do is the left-hand side of the grammar rule, that expr, we name our function for it. In our case, then it returns an expression that's a tree type. When you have a non-terminal like term, then you call the corresponding function. So somewhere there's a grammar rule for term, and so we wrote a left-hand side of grammar rule became a function term, and so we call the term function. And then let's see, the repetition goes to a while loop, but the terminals, like the literal token plus or minus, we look and see, is it this or that? In this case, the OR bar, you can see that showing up as a double OR bar. But basically, tokens, you match them. You decide if they match, and then you call next token to get the next one ready to go. And so our other term turns into that. And then the sequence, alternation, and repetition. So sequence is term followed by this, plus or minus followed by that. Alternation is the plus or the minus, and repetition is the braces. Those turn into code. Okay, so the sequence is easy. It's just one statement following the next. The alternation, you can see that in the while statement. It could be on an if statement, but it's somebody's making a decision. It's one or the other. And then the repetition is the while. So it's not hard to write this if your grammar's in the right form. Okay, there's a whole body of work on how do you get it in the right form, but it's not that hard to put it in the right form. It's not that hard to write it as code like this. All right, but I want to switch to a different approach. So we have, I don't know, a multi-hundred line method that's the syntax analyzer, the parser, and it consists of a bunch of methods like this. One per grammar rule. I don't know, there's 15 or so type statements, and then expressions have their own subgrammar. It's, I don't know, 30 methods or something. It's big by my standards anyway. All right, now we're going to try a different way, and that's the Parser Combinator way. And this is the new version. So the previous was the current approach. This is the new one. We'll start with the same grammar rule, and then the Parser Combinators, they look a lot like the grammar rule. So here we got expression equals term, and then and match plus or match minus, and pipe to make binary tree. So like what? So the left-hand side of the grammar rule defines a parser. So we're assigning a parser. The terminals and non-terminals refer to other parsers. So term is a parser. Every left-hand side has to become a parser at some point. And then the plus or minus, we have a match function that is a parser that matches a plus sign, or a parser that matches a minus sign. Okay, so all those are referenced. And then we have operators. So the separated by is sort of a fancy one, and it says, it's kind of like, I think of it as exponentiation. A and B is A, B, A, B, A, B, A. So it's A's separated by B's. Okay. In our case, they're separated by pluses and minuses. It could be a list of values separated by commas. All that's possible. Okay. And so we're looking for a term separated by pluses or minuses. So term separated by pluses or minuses matches the grammar rule. All right. The or else, well, A or B, that's my grammar or operator, matches A or B, but not C. Okay. And then finally, there's a pipe operator. It sends the results of the parse to a transformation function. And so in our previous one, we returned expression. We want to do the same thing here, where this thing should return an expression. So make binary tree will take care of that. It'll take the terms, the pluses, the minuses, and assemble them into a binary tree. So you can see this is a lot more concise. I mean, we still have to write make binary tree somewhere, but the grammar is much more direct translation from the sort of original grammar into our Parser Combinators thing. So now we'll see how it goes. I mean, this is we're doing this from scratch here. I didn't pre-do it or anything, so you get all the glitches as well as the good. Excuse me. So the evolutionary approach, it's one of the ways you can transform, kind of make a big refactoring happen. And this one is, when everything's compatible, we start with the original parser, then we're going to move to a version that has mostly original but some new parser, and keep going until we got mostly new parser. And then at the end, we got only new parser. We can get rid of all vestiges of the original parser. And with this approach, we can release at any time. Every intermediate version is fully working. So I may make some mistakes putting a rule in or something. We may find some bugs in the Combinator library for all I know. But barring that, it should be almost always releasable. Okay. So we start working, we keep working the whole time. This is why I like this approach the most, because, I never have to worry that I'm going to have a bunch of broken pieces lying on the floor and, wait until I finish this. No, it's just all interoperates, and it's all a pretty smooth transition. Now, I don't have a big formal process for deciding whether I can do this or not, but I do have a few guidelines. So let's walk into that. So one of them is I look at interoperability. So I've got an old way and a new way, and I want to know if the old way can call the new way. So can we make it so recursive descent methods call our new combinator parsers? And I believe, yes, we can. I haven't done it, but I believe we can write an adapter that will do that. Can the new way call the old way? So can one of our new parsers reference existing rules? Again, I think we can do that with an adapter. Again, I haven't proved it. We have to work on that. Okay, now, so in terms of our project, I'm pretty sure we can write an adapter. The old, they're both trying to accomplish the same thing: turn the tokens into a tree, and there's nothing inherently conflicting about them. Now, in general, however, you might have a case where the old way could call the new way, but the new way couldn't call the old way, or vice versa. And if that's the case, you don't have as much flexibility in where you start. So because we can call old or new, in our case, in any order, we can pretty much start anywhere and do any piece and work our way forward. If we're restricted about old calling new or vice versa, we have to start either at the top or the bottom. And if we have recursive dependencies, we're going to be kind of in trouble because, it's sort of got, well, A to B to A, you're back around calling yourself. So one way or the other, you're going to be calling, if B is old or, B is new or whatever, you can't avoid calling back to the old. Okay. So, you'd have to put some indirection or something in. It might not be possible, but, it might work. All right. And then if the answer to both questions is no, I can't call old or new from each other, this is probably not going to be the ideal approach. You might be able to do something to kind of evolve forward, basically evolve one implementation into the other, and then sort of plug in the new one. But it's extra time, or you end up backtracking and that kind of thing. So, we don't want to be in that position. We'll take a different approach. But again, for us, we think the answer is yes on both cases. It should be pretty straightforward to interoperate. The next thing I might look at is just kind of the two approaches and what's similar and different about them. So if I look at input, the original parser, you have array and index and actually a current token. The new parser takes slices of arrays. So a slice is really, array plus index is practically a slice anyway. So they're pretty similar. I'll migrate if necessary, but I got a feeling like I don't think I have to do it. I think given the adapters, we probably don't. Then I might look at the processing. So the original is recursive descent. The new one is top-down backtracking. It can handle slightly more ambiguous grammars than recursive descent, I guess you would say. But at any rate, those two approaches they're somewhat similar. They're both top-down approaches, but we're going to do it with adapters, I assume. I'm hoping. And so we won't actually try and implement something that's a combination of recursive descent and top-down in the same method. It'll be either a recursive method or a top-down new method. All right, more on processing. In the original parser, we combined parsing, tree building, and analysis. So we had that loop, and in the loop we were capturing results and putting them together into a tree and all that stuff. In the combinator approach, parsing is its own thing. Tree building, you pipe to a function that does it. Analysis, same thing, pipe to a function. Now, one thing that may happen, we could find that our original parser might benefit from that approach of separating out the tree building and analysis. We may or may not do that, but if we did, you'd have a method that presumably could be used by both approaches. So that'd be nice. And then finally, the output. In the original parser, we returned, we called it parse structures, but statements or expressions in general. There are a couple others. We're returning a tree structure. And if we fail, we throw an error. And then the new parser, we have a parse result. And it's an enum. It's got a success case that returns the tree and the rest of the input, and a failure case that returns the location and message. We could migrate our original parser to parse result, But again, I'm only going to do that if necessary. And I feel like the adapters are going to make a lot of this not so necessary. So I don't think there's any inherent conflicts that we can't work around if we had to. But I mostly think we won't need to worry about it. The only place is the adapter is going to have to deal with this stuff. I mean, one wants a statement, one wants a success enum. It's like those are just not the same. So we'll have to make sure the adapter handles that. But I think we can isolate that in a couple of methods and call it a day. Then the last thing I might look at is other opportunities, because we're in there doing things like, is there stuff that would make life better anyway? And it's strictly not part of the evolutionary process. It's more just like, oh, there's stuff we could do. All right. So I don't know. I had a couple. One of them is there's some goofiness around unary minus, and when you have an expression that starts with a unary minus, like, how do you know it's a unary minus, right? It's like, well, if the thing before it was a right parenthesis, it must be a regular minus. And if it was a variable or a number, I don't know, there's rules. Maybe there's something we could do there. Another thing is we might be able to, the expressions are moderately complicated, because basically when you do this recursive descent approach we did, if you stay within that, the way you handle precedence and associativity is basically create one grammar rule per precedence level. Okay, so we had term plus term. There's also factor times factor and condition and condition and stuff like that. There's multiple operators that have multiple levels. I don't remember how many there are, but I think it's like 6 or 8 levels. Okay, and I don't know, a couple of years ago, I worked through a Dijkstra-Shunt-Yard algorithm. It's an algorithm that handles precedence and associativity with a simple grammar rule, like expression goes to expression operator expression or something like that. And that algorithm could replace those 8 levels of grammar rules with a little table that says plus and minus are associative and lower precedence than times. Okay. Again, it's nothing to do with the transformation we're doing. It's just looking around and saying like, oh, while we're in here, is there something we can, get from this? All right. I don't think I'm going to make that part of this project, but maybe we'll pick it up another time. All right. So let's go see what we're up against on the code side. All right, so let's put this over here. This is the interpreter, okay, and you can see there's a lexer, a parser, and an interpreter, so corresponding to those 3 parts we talked about. We left off, basically we had something, we ran, where's my example? This amazing and horrible program. It builds a maze, and what's cool, and I don't know, it's just, I have such a mixture of emotions about it, but a lot of statements look like this. If some condition, then go here. If some condition, go here. If some condition, go here. If some, you're doing this all the time, and then you'll get to the bottom and it'll be like, oh, Q equals 1, now go here. All right, and it just goes on like that, and yet it draws pretty cool mazes. Okay, so, we can run that program and see. Let's see. But yeah, maybe I should do that. I haven't done it in a while, so let's see what we do. I guess we're going to run. We're running our redevel print loop. We're not running this. So I copied this. We'll paste it in, give it a go. I probably should have done that once before so it didn't have the slow startup, but there you go. All right. So when you start out, you just have this default end. I'm going to paste in the code from that basic. Okay. That. All right. And we'll run it. Okay, width and length. Let's do 10, 15. All right. So it produces a maze. So uses I-bars and this, but you can see it's a legitimate maze, and Yeah. If you were better at mazes than me, you'd probably get through the whole thing. But anyway, just an old random game program from, I don't know, 1980s probably, maybe 70s. Creative computing, amazing program. All right. So we can run stuff like that. Now, the focus we have is the parser. So let's go in the code side. So here's parse. This is these are the structures that we're returning. Okay. Oh, we got parse error. Okay. I think we called it parser error in the other, but parse is the top level. It says a line of code is a line number and a bunch of statements. All right. And then we have expressions, form a tree. There's sort of base cases like these. And then, the core of it is op1, op2. This is a binary tree with two expressions in it. So you can see it's a recursive type, and the indirect here handles that. So, I mean, this is quite the statement in Swift, right? It like gave us a whole tree structure for practically free. I mean, just for the cost of describing it. If you think about what you'd have to do to write a tree for expressions and so on in C, like, a lot of work. Even Java, fair bit of work. But we have those pieces, and we can define functions on them and so on. Right. Then we have dimensions. For arrays, they have a name, a dimension, and a type, like int or string. Printables, you can pass semicolons and commas and so on. And then finally, statements. These are the statements in BASIC. So there's an assign, a data, a def, end for, go to, whatever these are. So what is that? 105, 86, is that 19, 20, 18, somewhere in there? Okay. Every one of these, every statement you write turns into this, and this is the tree, and the interpreter is going to look and say, oh, you had a go sub to a line number. How do I do that? Well, I push it on a stack, and I do this, and I do that. Okay. All right. And I think, that's basically it. So when I say we return a tree, we're returning one of these structures, depending on the level we're at. Okay. Then the parser, let's look at its state. It knows its lexer. It has a current token. It keeps track of the line number and column number, and then it's got a little helper data structures here. All right. Then I have some methods to let me require a particular token or a variable and so on. And then the high level entry point is parse. So you give me an input string. I will call the lexer on it and then prime the pump, as it were, with next token and call single line. And my goal was to produce a parse, which, if you remember, was a line number and a bunch of statements. Okay, so single line tries to do line. Okay, and line says, well, if you start with an integer token, I'm expecting an integer token, basically. If you have that, then I create the line number, read the next token, and then I call statements to get all the statements. Okay, if you didn't have a line number, then we throw an error. Okay, line number is required. All right. And then statements. Okay, so I'm not going to go through every single one of these, but we'll go through the top a little bit here. Statements returns an array of statements, and it does that by parsing statement. So let's see, here's statement separated by colons and more statements. Okay, so if you remember, we had a separated by rule in our parser combinators. This one's going to be subject to that. We got statements separated by colons. All right, and then let's go into statement here. Yeah, so statement says, I'm looking at the first statement or the first word in a line in a statement. It's either data or def or dim or end or for or go sub, etc. And basically, I have a method for each one of those rules. Okay, the grammar rule for go sub. Okay, and so on. All right. And then the whole rest of the thing, I don't know how many lines, looks like 769 or 68. Okay. Every one of these, I mean, pretty much every one beyond we had a little bit of stuff up top, a couple helpers. We have a couple helpers down here, type checking and compatibility. But for the rest of it, most of these rules, most of these functions are trying to match something. Okay, they match and they return an expression or a statement or parse. All right. Let me get the p combo in. Okay, so p combo. This is what we worked on in the last few weeks. We made a 1.0.1 release, but this basically defines a bunch of grammar rule operators. Okay, and we saw this one and we saw this one. Okay, but we would we could use any of these. All right, and we saw this pipe operator. Okay, so this package I'm going to try and pull in and use it in our system, basically pull it in and use it. Okay, so, and I have not done that a lot. So let's see. The other thing is, even though like not never, but I rarely use branches, but I'm going to create one here, and I haven't done it in Xcode before, so I don't know what I'm up against. Source control. Well, I'd like to work in a branch because we're doing this EVO approach. I'm going to unroll it at the end and take a different approach, and then eventually we'll pick one and keep it. That's the current branch. New branch from main. Okay, that's what we want. All right. Yeah. I don't think we care about the to-do, so we'll just take that. So let's do a new branch from main. I'm gonna call it Evo. Create that, and that's the current branch. Okay. All right. So let's go back here. I shouldn't have anything to do. Okay, base int. Yeah, that's fine. Keynote file. All right. So what I recall is I think you add packages. GitHub, no. Oh, how do I do this? No. Recently is pcombo. Okay. Yeah, GitHub com p wake pcombo. We're going to take the main thing. I'm going to take this add package. Okay, this should put the library in our application. Okay, that's the right one. Okay, now where does it put it? There it is, down at the bottom. Okay, we got pcombo main. All right. Let's do, well, we didn't do tests before. Let's do that. So I should be able to just Control U, Command U. Okay, so it's got to build it. It's got the new library to build in, so it's going to take an extra little moment here. Okay, 293 tests in not much more than a second. The tests have really been running quickly lately. I don't know why. I'll take it. Okay, but let's commit. Okay, we haven't. I don't know if this matters, but we'll take it. We haven't done anything with it, but we added a library. Okay, so I could release. I mean, this is my private project for now, so nobody's relying on it but me, but I could release at this point. There's nothing, my tests are all passing. It's got an extraneous package in it, but nobody cares. Okay. Users wouldn't see it. System might be a little bigger, but that's okay. All right. Let's see. So I want to do something easy to start with. So let's see. Let me go back here. So when I look at these structures we're producing, parse depends on statements. Let's go down to statements. Statements, well, line number, column number, and string, those are all pretty primitive types. Type is primitive. Expressions, statements depend on expressions. They depend on dim infos. What was there? Data, string, okay. Printables, and so on. So the statement clearly has dependencies. Now, printable, well, it has primitives, but it also depends on expression, okay? And then dim info also depends on expression. And let's see what expression depends on. These are kind of the base level. If I think of it like induction in math, there's sort of base cases and then recursive cases. I guess, or I can think of it like recursion. These are recursive cases because they reference expression, but they're referencing name, type, token type, float, string. Those are all primitive types, or not. Well, float's a primitive, but token type is not depending on expression or statement or anything. It's from our lexer. It's kind of a base level dependency. So what I see is expression depends on expression, but not on anything else that is recursive across these. Whereas statement and dim info and all that, they depend on expression too. So in some sense, statements are up high and expressions are down low. They are recursive, so there's some challenges there, but we don't have to worry that if we handle an expression, we're going to end up dealing with statements. So it's probably easier to start with expressions and work our way back to the others. But again, it doesn't matter in some sense because we got that full interoperability. It's just kind of, for me, keeping sense or keeping track of things, it's probably easier to start at the bottom and go to the top. But actually, I'm going to change that a little bit because I've got some statements that are like really trivial. End is one. The end statement is just end. There's no, there's a line number, but there's nothing else. Another one, restore. I saw, oh, well, there's REMARK too. Oh, REMARK turns into a skip. Okay. Restore, and I think maybe return. That might have some complexity, but skip and stop. Okay. So we've got 3 or 4 statements that have no values on the right. I think maybe it would make sense to do them first. They're very simple as statements go. So let's do one statement. Let's do these simple statements, and then we'll move into expressions. So the reason I like the statements, they don't depend on anything, so I don't have to worry about if I call the new way, could it call the old way back? Whereas with expressions, if I replace one piece of the expression with the new way, it's recursive, so it's eventually going to call back to the old way again. So, let's just do one side first. Okay. Let's see. So in parser, let's get down to statement. Okay. So we come in, and basically the first token tells us what kind of statement it is. Okay. And so let's see. Let's take a diversion again. Sorry, it's diversion. I want to look at the tests and see what we're up against there. So the statements, okay, here's the end statement. All right, it calls parser.parse. Okay, so parse is the top level entry point and returns statements, line number with a series of statements, and this parse. Okay, and so that means if I do this change, parse the old way is going to have to call the new way. Okay, let's see what else we have. Some errors. We've got to check one statement, And a lot of these call check statements. All right, let's see what these are. Okay, so here's check one statement. Give me a program and I will make sure it gets the expected statement. Okay, and check statements is doing the same thing with an array of statements. All right, and we have a check expression that puts the expression in a program and then verifies the value of it. Okay, so what that means is our tests, at least with most of them, are they're coming in at the very high level, the parse level, and we don't have to worry that we're not. Can't say we're not doing any, but we're not doing a lot of jumping in the middle of the parser structure and trying something out. Mostly we could put them in programs and see that they work. Okay. Oh, and I should say one more thing. I don't my chart of comparisons, I probably should have said on the error messages, I don't care if I can get exactly the same text, but I don't want to lose any errors. You know, I don't want my new parser to ignore errors that the old parser caught. Okay. Let's see. So in here, yeah, what's weird to me is this is really, it's refactoring, and yet I just kind of have to jump in and do it. It's it's kind of crazy to me. All right. So somewhere, let's see, where'd pcombo go? We can see some examples. I think bind has an example. Okay. So you can create a parser. We've got this satisfy as sort of a base parser, and you just create an expression with these. Part of the issue, let's see. Let's look at the code. This thing is called parser, okay, and it's a protocol. So I've got a name conflict at the top level over here. So let's change this for now. It is a parser, it's true, but I'm going to change the name to syntax analyzer. Or I'm open to suggestions, but I just want to get it out of the way so it's not parser. Okay, it'll rename the file. Run. Okay, we'll run those tests. Good. We'll commit, refactor, rename, parser to syntax analyzer. Now there's probably a bunch of variables that say parser. I can live with that. Eventually it may not matter, but just to avoid this kind of conflict here. Okay, now we're going to have to import pcombo. Okay, now you might be saying, do I need any new tests? Well, in a sense, I don't. Everything we're doing is going to test through existing stuff. So in that sense, I think we're okay. And let's just start. Let's create a parser first. So let one word statement. We can come up with better names, but this is going to be a parser in the pcombo sense, and it's going to match. I forget what we said. End remark. Restore. So yeah, this one result equals restore. Yeah. So these one word ones, they just do next token and result equals. Okay. So I'm kind of trying to define what do they look like. I'm going to say it's well, okay, this doesn't exist. I'm wishing it into existence. Any of, and now I'm going to take these token words. Okay. And again, this is not existing. Any of end, remark, What was there? Stop. There were more. And remark, restore. Return statement has more going on, so maybe we won't do that one, even though it's a one-worder. I guess restore. Okay. I'll leave them alphabetical for whatever reason. Okay. Okay. So if I match any of those things, I want to pipe that to some, because my result is supposed to be a statement. This is a token. We've matched a token. I need to convert it into a statement. Okay. And so, let's call it simple statement. Okay. All right. Now this won't compile because this is not defined. This is not defined. All right. I don't know. Maybe this would be better. Okay. Let's define any of function any of. And I don't remember how you do it in Swift. Is it dot dot dot? Token. Oh, I'm gonna have to look. I assume there is a var args, but that's weird. I'll pass an array if I have to. Yeah, dot dot dot. Okay. Tokens is token dot dot dot. And it returns a parser. Okay. And can only be used. Ooh. Okay, well, I think we have examples. Pretty sure the package includes the tests as well. Do we have source? Yes. Trying to find a good test. No. Oh, this one might. Okay. Match. Turns. Oh, yes. Okay. Yeah, we got to qualify it. Okay. Turns satisfy string. Whoops. Boy, I just can't hit my keyboard today. Satisfy, in our case, token. Okay. And satisfy, we call satisfy. We get an argument that's the token we're trying to match. Oh, and this is actually token types, I think. Anyway, the argument we're trying to match, well, we want to match value or value or value or value. I'm pretty sure this is token type. Let's check our statement. Token.type, yeah. So this, and we want to say satisfy with tokens. How about set of tokens? Can I do that? Dot contains $0 dot token dot type. Is that how we set it down there? Yeah. I guess I have to spell it right. Okay. You might wish I tested it directly, and we maybe should, but we'll get there. Okay. Now, a simple statement, that's a transformation function. Okay, so simple statement, and it's going to be given a token. Token, and it's going to produce a statement. Okay. Right. What's your problem? Cannot find operator. Oh. Isn't that right? Ooh. Did I not make something public? Oh. Okay, so I'm using it here. Let's find pipe. Public class pipe. These aren't public. Okay. All right. Yeah, this is the sort of thing I was afraid of. I don't want to have to do a lot of this, but what are you going to do? All right, let's compare and then get down there. Public func. See, so yeah, I left out something that should have been public. Ugh. Okay. But that's getting us there. Okay, and let's just return well, let's return statement.end for now. Okay, an implicit return. All right, so we have a problem. This thing does not work as an operator. Well, I probably could work around it. Sorry, satisfy its pipe. Well, let's put a workaround in for now, and okay, we can define our own stuff. I think. You know, declared one at file scope. Okay. No, we're gonna have to fix it for real, I think. Okay. There. Okay, so that's gonna be waiting on that, and then our parser. Let's just do end for now. Start simpler. Okay, so if we match end pipe to simple statement and return end, okay, that should be okay. All right, so I'm going to shift gears. Well, let me do this much. Okay, I'll take this out for a moment and just make sure I build. All right, and then here's the pcombo project. I don't have a good test. I mean, I know this needs to be public, and that tells me I should at least check these other ones. Yeah. There's no function for that one. Check has an operator. That's public. Mosley didn't forget. Public class. Separated by, okay. Let's run these tests. Okay. I need to tag. Let's see. Do I push first and then tag? Okay. Make operators public. Okay. This tag main 0.1.1. And push again. Include the tags. Okay. Now this guy, I think I can say update package. Update succeeded, good. And now back in here, should be able to uncomment this and build and run tests. Oops. Property initializer. Let's pull these out. Okay, again, I'm going to look at my example. You'd think, being that I wrote this stuff, I would know more like what's in there, but it blurs too quickly. Okay, so grammar tests. How do we do that here? Well, it's a little different situation, isn't it? Can I use instance within property initializer? It's funny because they don't do anything. But let's pull that inside. Okay. So we have this. Okay, so we have a rule that matches one case. If it matches it, we want to return it, the result, and if it doesn't match, we want to fall through and do our normal stuff. Okay. I'm torn because on the one hand, I've got this thing that's high level test. Well, not high level, but medium level. You know, the statement tests that go through and it will do the thing. Maybe let's just write it in line and see what happens. Okay, so no harm creating a parser. We can let parse result equal one word dot parse on. Okay, what's our input? Well, input in here, it has to be an array slice, but we have an array because that's what we're working with up here. Token. Let's see, where's, oh, there. Token. Next token. lexer.next. Oh, that is different. You know, we pulled that back into the lexer, and I think that might be a mistake. Gonna go to the top of the lexer. Okay, we got tokens. Sorry, predefined functions. Okay. Here we have the program string. The index into the string. We don't care about that. I could have sworn, I thought we produced an array of tokens, but that's not what I'm seeing here. Okay, they're less compatible than I thought. I could have sworn we did that. Okay. I think these are all just finding tokens here. Okay, well, maybe I need to, maybe I should test this in after all. What I'm thinking of doing is calling next token, basically filling in an array of tokens. Where's next? Okay. Whoops, sorry. All right, so this thing returns an end token at the end, and I can get them all. All right, let's do that. Okay, and I'm gonna expected expression in list of statements. Let's hold off on this. Okay, so we're gonna back off our parser again. The story of what's going on here this morning, and I'm gonna change the loading. I got next token. I want to change next token to return from an array of tokens rather than letting the lexer own all that. Okay, and part of this is only doing this parser, because it's doing basic, it's just doing a line at a time. And so parse, remember, returns a single line, a line number and a list of statements. So, all right, let me make one more change in here. The tests, parser tests. Let's make a rename here. No, let's leave it. Sorry. So what I think I can do is let's define tokens. Yeah, I mean, again, it's like it's a refactoring, but it's not a by the book refactoring. It's sort of a replace algorithm refactoring, which is like do your thing and then swap it over. All right, but I'm going to say I've got tokens is array of token. Okay. And what I'm going to do is pull them all in at the beginning. See if I can do this in one modification. Well, I'll do this for now. Okay. Right. So everybody funnels through next token. Let's maintain an index. Okay. And again, nothing's going wrong yet, but it's about to. Let's make next token okay. I'm going to append append token. Okay, so I'm going to accumulate them as I go for now, and then what next token to pull is that? Can I do that? Okay, again, I'm trying to take little small bites. No one's using index, no one's using tokens, but I'm accumulating them. This index 1. Maybe this starts, let's start this at -1. Okay, and now I can say tokens subindex. All right, this should be a neutral change. Okay, so I'm just writing into the array as we go, and I'm fetching the one I just wrote, and there's no harm there. Okay, now I want to move this into the front. And move that. Token equals token subindex. Let's go back to 0 here. Much more natural feeling to me. Okay, so get token subindex and get the next index. Okay, that feels right to me too. Okay, so now I want to move these all to the front. Okay, and this is definitely one of these refactorings where I'm arguing my way through it. But my claim is lexer. So lexer.input, when you start calling next token, it reads tokens until it gets to a token dot end token or something like that. Let's find the value. At end. Okay. So we can read all those tokens till at end, load them into our array, and do that. And the argument is all the next tokens together they always read through the value coming in. We're sort of changing reading from one at a time to loading up the list of tokens. Okay, and that way getting to the slice will be simpler. Okay, so this stuff I want to do up in here. Okay, so I want to say the current token equals let's do var. Well, it's not an add end. Do that, and current token lexer.next. Okay, so I believe what I've done here is I have gone to the lexer, I've fetched every token, appended it to the end, and then the add end token, I append that finally. And so my claim is these two lines don't belong here anymore. Okay, now when you ask for the next token, we assign it and increment the variable. So rather than talk my way through it, I'll run my tests. Oh dear. Syntax error stops interpreter. Okay. Interesting. Control flow test. Why would that care? Whoops. How about this? Well, let's just run this one test. What? I'm puzzled. Okay. Interactor. Put output strings. That shouldn't be anything. Okay, let's break here, I guess. Of all the places, see, this is interpreter test. So this is after we've already done our syntax analysis. I'm definitely puzzled. Oops. Stop. Okay, so let's look at program. Oops. Ten print. So this is illegal because the braces can't be done there. Okay. And outputter shouldn't be anything interesting about that. Oops. Okay. We'll step in. let's step over. Okay. I was trying to get here. Maybe it's blowing up before it gets there, though. Okay, let's stop. Break here and here. Run this. Step over. Okay, interpreter.run. We'll go into that one. Let's see, run loop. I think we can get there. Apparently not. Come on. Well, I could have sworn we got that far before. But we seem to be balled up. Are we getting here? Yes. Okay, he's got lots of stuff in him. All the predefined functions. Okay, we've got a program line. There's the parser. Okay, I don't see why I can't step into here. Okay. Oh, what's that doing? Okay, it's taking the program, it's sorting the lines, it's parsing each line, and for each parse, it's running through oh yeah, this is pulling all the data statements out of the program, which there shouldn't be any. Huh. Okay. Run through the statements. Find the statement at the index. If it's a data statement, then append some stuff. Otherwise. Okay, so make sure we're where I think we are. I thought I had a few. I guess I'm not actually stopped. I'm just running. Okay. Let's pause this. Okay, I guess gather data is part of interpreter. Okay. Let's make a new test. We'll stop this mess. Gather data. And I guess at the end, this should be interpreter.data. I'm assuming this will blow up the same way. Okay. I don't understand what the interaction is that's causing the problem. So maybe we need to test back a level and see what our statement looks like when we parse that thing. Let me make token error. I would expect that to be in there. Oh, I think I know what's going wrong. Notice these, let's see. The index, I think the index is not being incremented on a bad error. Why this wouldn't show up till now. All right, let's look at num variable. Actually, these are even easier. If you find it, return it. Index. Index. Offset by index. Handle variable goes +1. Okay. Yeah, my theory is make token with error. I think these other ones increment the index, but this one doesn't. Okay, so it skips past the quote, skips past all the stuff. Most errors will, well, string errors would fall through and still increment. Okay. So, all right. Tell you what, let's take a break, a 3-minute break. I think we'll come back and we will. I have a theory of what's going wrong, so I should be able to test that more directly in the lexer test. Okay, and then the control flow test, because I think what's happening. I think, well, my theory is in this case the syntax error here ends up being stuck at this position. Now, why my change triggered that, I'm less sure. Lexer, okay. Yeah, I'm not clear why that doesn't show up until we tried to fetch all the tokens at once. Maybe it just blows up. Yeah, it may just be that it's blowing up. The error return early gets caught earlier, and so it's never an issue. Is maybe what's going on. All right, 3-minute break, and we'll come back and see if we can isolate this error and fix it. All right, welcome back. Let's tackle a lexer test. We must have some here. Okay. Check token. Test end. Let's put it here. Func test index moves after error token. Oh, interesting. Okay, so I think our check token it looks at the token, but nobody's looking at the token after that. Okay, so what I think we should have is let's make an input. Yeah, let's do more like this one. Let lexer equal lexer of, well, let's just start with this. That should be a bad token followed by an at end. Yeah, lexer empty. Token next is end of line because it inserts an end of line no matter what. So probably should be followed by at an end of line. Okay. But this test is pretty close. Token 1 type, yeah. Token type should be error. And then we do token 2 equals the next one. Should be end of line. And then token 3 should be an end. Okay. Given that input, we expect to see an error followed by an end of line followed by an at end. Okay. And let's look at error. Token type is just error. Okay. There is a string message, but that's fine. Okay, so lexer test. Okay. So my prediction is this test fails. I think it's going to freeze up. No. But, oh, okay, it does fail. It doesn't freeze up because it's not looping over them. It's just checking one at a time. But we get an error and an error. Okay, so it never moved forward. All right. I think that we can deal with. Okay, make token error. 1. Okay, and again, if I look at like number, all these ones, they skip over. They move the index forward. So let's index repeat any. Okay, so yeah, whenever they're there, if they consume a character, they move it forward. All right, is my argument. You know, it's not working, so this should work now. Okay, and then I believe this should work. Okay, and this should work. If I take out the breakpoints. Gonna hit every breakpoint. Okay. Okay, interesting. Somebody failed. Was it this test failed? Okay, what do we get? No, 0 line numbers required. Found at end. Oh. 0 line number is required. What? Assert true was question mark. 9990 line number is required. Oh. Okay. Let's make sure nobody's infinite looping at this point. Okay, 1 failure. Output. Okay, starts with 10.7 expected start of expression. Okay, so I think let's we're no longer failing on gather data. I think we're failing in our program now. So let's run this test. We'll step in. I'm going to break here. Okay, yeah, no more gather data problem. All right, parse 0, nothing. Okay, parse is that's the current program, right? No statements, no line number, basically. Okay, then we go look up the first one and try run loop. Okay, so let's break here. And step in. Okay. So print, whoops. Location, line number 10, part 0. Okay, so program sub line number is 10, print junk. Okay, now parser.parse. So parse error. Line number is required. Oh, that's just so weird. I wonder if it's that. I think, like, when does it establish the current line number? Maybe it's failing to do that because the whole statement has an error. It should be the token that has the error. I wouldn't have expected this message for sure. If anything, I would have expected a message that there was excess tokens after end of line or something like that, which I'm okay with some changing messages and stuff like that. I think we're going to have to step into this parse. Yeah, we're going to have to step into there. Okay. Step in. Continue. Continue. Okay. Let's check line. Oh, darn. Print line. Line print 10. Okay, let's step in. All right, I want to go here. Let's see tokens. Line 10, integer. Excuse me. So there's the line number. Then the print. Column 7, error, unexpected character. That's what we expected there. Oh, another unexpected character. Okay, yeah. Then the end of line. Then the add end. And then line 999. Has an end statement, an end of line, an add end. Well, where is this coming from? Line 10 again? It seems to be in there twice. Let's print the input. Put line 10. Well, maybe I'm looking too far with add end. Maybe I should just be looking for the end of line. Although we seem to have an add end, right? Let's go back up to print unexpected character, left paren, right bracket, end of line, add end. So how do you get two of these? Okay, let's. All right, let's try again. I mean, I gotta say, error handling is kind of the worst. but no excuse. Okay, let's see. Input. Oh, God. Oh, I can see it on the left. Print 10. Okay. Let's print lexer. Probably too much information. Yeah. 10 print that. That's the actual stuff we're trying to input. And a new line. Okay, so that's what the lexical analyzer is going to work with. Okay. Move self-submit much current token. All right, let's step over. Current token is now the line number 10. And we'll append that and get the next token, which is a print. Append that, get the next token, which is the error. Current token.type equals error. Second error. I feel like it went too far, did it? Unexpected character, end of line. Okay. We'll store the end of line. We'll get the next character, add end. Token.type is add end. Jump out, append, next token. Oh, did I not seed the token? Print the index. 0. Print the tokens. Add end. That seems fine. Parse lexer input. Let's print token. It's unknown still. Okay, but if we do our step over, token should now be line 10, the line number. Okay, and we should be going into single line. Over. What? I'll step out, but what happened there? Over. Wait a minute. EVO. At end. Whoa. Okay. Something's... I'm doing this test. Oh. Okay. I'm not resetting. Woof. Okay. Yeah, so I haven't been doing my to-do. Let's do that. Okay. So we want to let's see. We want to introduce a new style parser for the end statement. Okay, and then to do that, we needed to convert token reading to work a full line of tokens at a time. That's what we're trying to do here. And then we were fix a bug in lexer that didn't move forward after illegal character. Okay. And I think we'll skip this. BI-22-40. Well, no, this is EVO-22-01, August 8th. Okay, so a month ago, we were doing that stuff. All right, we've fixed this bug. Now we're reading a full line of tokens at a time. Okay. Delete these breakpoints completely. Somewhere there can do this in one swoop. All right, so this is setting up the tokens. That is there. This should be good. Okay, so, well, we got two changes in there. Okay, fixed defect in lexer where it didn't move forward after an illegal character. Why that wasn't visible, maybe we were detecting the error sooner. Yeah, I think that's what it is. So we were in the original approach, we never tried to read all the characters in a line. We just read as far as that first error, and then once we saw an illegal character, we said, "Oh, it's a syntax error, return," and didn't need to read the rest of the tokens. Now we're saying, let's read the line and then decide what to do. Well, reading the line hit that illegal character and just kept returning the same token. So, all right, I feel like I understand what happened. Okay, now back to where we were. Okay, so the reason for all this, which we'll clean up at some point, but I mean, it's part of the initialization. So that is now we have the current token is token subindex, and we have an array we can slice. Okay, and the reason we need an array we can slice is because our new parser wants arrays. Okay, so let's check this thing out. So we create this. Okay, it's going to do its any of parser and match the statement. We're going to get a parse result back when we call parse on our input. Well, our input has to be an array slice. Okay, so let's see, where can we see that? Down in here. Parser definition. Okay, the protocol says you have a function, it takes an array of inputs and produces a parse result. And it doesn't care what your input type is or your target type is, it's generic over them. All right, and so this statement, let's statement, wherever it got to. Okay. Down here. Okay, 140. All right. We're doing this. Well, any of end, we want to parse tokens. Okay. And where do we get tokens? Well, that's that tokens list. And we want to start from the current token. Okay. So tokens is our list of tokens, and token sub index. Let's see, we've got the next token already. We may have to adjust. Okay, because this is a difference in philosophy, that the recursive descent one likes us to have a token sitting there ready to go, and we moved index when we got that ready to go. So index -1. So if we're on token 0, the first token, and the index is 0, we read the first token in. Now the current token is, well, let's say the end statement, and the position, we've indexed +1 past it. So we've got to undo that. In the end, we'll get rid of these -1s and all that stuff. But I think this will become isolated into one adapter method. All right, but index -1, ... It says make an array out of the rest of the tokens, starting there. Expected comma separator. Expected expression in list of expressions. Tokens ... No bracket. Brace print here. Okay. Build. Good. Okay. So now we have a parse result. All right. If the thing is, on the new stock combinator, it returns us the slice of the rest of the input. We can just ignore it. If the parse result well, we have to do this funky stuff. Okay. If case success, and we get a statement, and the remaining input, yeah, we'll have to know what that is. Okay. Equals parse result. Okay. Cannot find remaining. Oops. Let remaining. Okay. So my success case, if my parser succeeded, it returns me a statement, because we said simple statement, and it returns the rest of the input. Okay. So the remaining, well, in the end, we're going to return statement. Okay. If it succeeded. Okay. If it succeeded, it moved the index forward, okay, by 1. And this is the part I got to get right. All right, but somehow I have to adjust index. Okay. In this case, it moved forward by 1. Well, it's remaining dot start index. So the rest of the input starts at start index. Okay. And I think this is off by 1. Let's see. So I gotta. Okay. Let's say our tokens is 10 and. Okay. So that's really an integer 10 and an end statement. and an end of line, and an add end. Okay. That's what that input will generate for us from the token perspective. Okay. And our index is, when we come into this statement, index is 1. And, well, token, sorry, let's get this right. Here's 0, here's 1. Index is 2, but token is .end. Okay, so the current token points to the index here, and then the index points to the one after it. Okay, so index will be 2 when we start. We take -1 because we're trying to get to this one. Okay, and then our parser will turn index into, matches that from 1 and converts it to 2. So I think it leaves our index there. And then it says the index is 2, and then we have to do a next token. Okay, and next token is going to grab, reset the token to 2, and then change it to 3. Okay, 140-ish. Okay. If I didn't get the next token, I'd still be sitting on an end token, even if my index was at EOL, which would be a mess. Okay. Now, if this was unsuccessful, well, it returns an error message, and we presumably don't move forward. Okay. And in our case, I think that's what we want. We just want to say, oh, this failed. We'll fall back to the old way. Okay. Now, what's the complaint? Immutable parse result was never used. That's incorrect. It was used right here. Okay. All right. Let's run tests. I believe my test should pass. And then we can clean up and generalize. Oh my goodness. Okay. Yeah. So make the end statement be processed by a new parser, by a combinator parser. Okay. So all that prep, and I think we finally tipped over. All right. So one thing I want to do, like I'd like to get rid of this. I don't know. I'm going to have a -1 somewhere, I think. If my int index, right now my token index is 1 ahead. Sorry, how do I say it? My token index, my index is always 1 past the current token. Could I make my index be at the current token? Would that be an improvement? And we started to do that with the -1 initial value, which I think is goofy, but maybe that's what it's going to be for now. And then I would add 1 and then fetch the token. Okay, so this change is saying index should be -1. -1, and we're experimenting. Did we push? Yes. Okay. All right. So -1, -1, but the next token needs to increment first. Okay. So now the index is always the same as the index of the current token. All right, so what does that do to our parser? Okay, now index is the same as the index of the current token, so this becomes index. That's an improvement. Okay, so now in this case, token is 1 because that's the current index. Okay, and we come back. Let's see. We come back from end. We pass the slice with this. Okay, that's good. We come back and the index is 2. Remaining start index. Okay, that seems fine. Now we're incrementing index though. So let's just assign token equals token sub index. That's always the case. Okay, so if I've done this right, this should just work. Okay, so make the token index be the index of the current token, not the next token. Okay. A little goofy, but it's going to help us. All right. Now, I want to generalize. Okay. And so I think this bit, what's he doing? He's either... Well, he's falling through if he doesn't. So that's sort of a second control flow, right? I don't know what to make this be. I almost want to be like return statement question mark. Okay. Let's do that. Okay, so I'm trying to make this into a method that returns either a statement or a nil, and then when I get back here, I'm going to do something if it depending on that case. Okay. So let's say let not parse result, let the statement of type statement equal nil. Okay. And then here I'm going to say the statement equals statement. Okay. And then here I've either got a statement. If I have a statement, if this thing is a statement, if the statement not a nil, then I'm going to return it. If it is a nil, I'm just going to fall through. Okay, no, it's not nil, so we can return it. Okay. Right. So this function, if I extract a method here, can I extract? No. Okay, let's make a function new parse of, well, it needs a parser of type parser. It returns a statement optional, and it looks like this. Return the statement. This is parser. Okay, give me. Oh, how do I have to do this? Oh, I know we do. Pull this back over. I think we pass parsers around, right? I do have to declare it this. This is where I think I felt like I should be using some SOME return types, and I never got that working. And I realized I had done some other stuff wrong and never kind of came back and tried again. But, okay, where I must pass parsers like in here, right? Parse. Oh, it's a class, so it kind of does the work for me. I really don't want to see. I really don't want to tell you the type of this thing. I don't care, honestly. Protocol parser can only be used as a generic constraint because it has self or associated types. Okay, I may have to work harder to get my adapter. I don't think I can put types on here. Input is token, output is statement. I don't think it'll accept that. Oh boy. All right. Well, I can. Let's see what the type of this thing is. It's probably horrendous. Let's do this for now. Get it working and then genericize it if we can. Pipe is ambiguous, cannot specialize non-generic type pipe. Is that going to work? Because I don't think so. Right, ambiguous, undo. Type is satisfy token and statement. Pipe is ambiguous, cannot specialize non-generic type. Pipe. Well, the worst is it told me that's what the type was. Pipe of satisfy of statement. Okay. Yeah, I really don't want to have to repeat this code all the time. That's just annoying. Why are you not happy? I think the answer is it's kind of a it's I believe it's a restriction in the interaction between generics and type aliases, maybe. But I mean, I'm trying to say this is a pipe. It takes a satisfy parser and a value, the value of type statement. So it's producing a statement. And so this parse result should be built over statement, and this should be fine. But it's not happy. Okay. And I think maybe I'm I'm going to create another class. I call it WrapNew. I don't know. Okay. But it's going to take some parser type, parser, and it's going to take a value type, and it's going to be here. Okay. And then it's going to need, oh boy. It doesn't need a function. Type alias. Well, I need this. There's my parser. I needed a init with the parser. Don't think I need anything else. Okay. And, whoops, where's... Do I need input because this uses it, and I need value because this uses it. Okay, and I need a function like this. I don't know. I'm not trying to be a parser, so I don't need a function. My parse, I don't want to get too balled up in them, but it takes an array of inputs and it produces, I think it produces a value question mark. Okay. Yes. Okay, parse of input. The result, let's make sure this has the type we expect. Parse result p.input p.target. Yes, we want the input type from the parser we pass in and the output type of the parser we pass in. Okay. Now, do I have to say where p.parser p.target equals value? P.target, the parser target has to be the same as the value type. I think. Okay, let's get these right. Now, where's my code down in 140? Down here. Well, I think this one's the bust, but let's take this code. And I'm going to commit a lot of sins to wrap this thing properly, so we'll see what goes. Okay, so we're going to parse result, parser.parse of input. Yes, that's inputs the array slice. Okay, so that first line seems okay. Then this is going to be good. Okay. Now, if failure, we're going to return nil. So we've covered the initialization there. And then if it's successful, I think we have to return the index as well. result failure, return nil. Result success. Value remaining. Okay. At the bottom of this, we got to return value. Okay. And then the index, I'm going to make the I don't think I have access to token, so I'm not going to try and do that. Okay. But I've got to get this. Let index equal that. That's the return position. Okay. So I'm not returning token. I'm gonna have to return something different. I think I've got to return value and an int. Index nil is going to return input. It doesn't really matter. We're going to ignore it, but input.startIndex. And this one is going to return value and remaining.startIndex. Okay. Have I done this right? Okay, so you try the parser, the new style parser. We're passing in a new style parser. P is a parser. Okay, you try the parser on the input. If it fails, we just return a nil and the current start index. If it succeeds, it gave us a value back, and the result type should be input value, token and value. Yes. Okay. And we return the value and the remaining start index. Okay. Now the caller is going to have to handle these two lines. Okay. Message was ignored. Yes. We don't need those. Okay. Now down here, I don't think we're going to need this. Okay. So now, one word statement. Okay. So I think what's going on now is we're calling let the statement and new index equal new parser. What do we call it? WrapNew. One word statement. Dot parse of tokens subindex dot dot dot. Okay. So that's the parse. We're going to deal this stuff when we get back. Right, that's fine for now. Okay, and then nope, these two lines. Okay, index if it's not nil, we're going to set things up for the next ones and return the statement. Okay, cannot find remaining. This is new index. Okay, this is awkward, but I think we got to handle stuff. Okay, so now this stuff goes away. All right, so we create our parser. We wrap it and call parse, and that gives us back a null statement or an actual statement and a new index. And we reassign the new index, so we move forward, and we make token equal the new index because that's always the case, and return the statement we got back. If it's nil, we aren't adjusting any indexes. We're just staying where we were. All right. Please pass. Digging a little deep to get these generics and associated type and all that stuff. Okay. Woohoo, because I feel like this is a big piece. All right. So we have a very generic wrapper that takes any kind of parser. We didn't put any constraints on the parser type. Okay. And let's move this down. Okay. Yeah, so we have no constraints on the parser type. You wrap it, you call parse, and it gives you back whatever type this parser gave you, which in our case, simple statement, is returning a statement. Okay, so if the first parser fails, it returns nil. Otherwise, it returns a statement. Okay, and we pass the right thing in. We adjust on the way out, and we are good. All right, let's clean up this junk. WrapNew is a little bit of an awkward thing. Let's go up there. Okay. WrapNew says, you give me a parser which produces a value type. I don't think I need... I think I could do this. P.target type. Take this out. Okay, so give me a parser, and I will give you a method. Give me a parser, and I will give you a method that produces an optional whatever value it produces in an integer index by calling the new style parser, but you can call me in the old style routines. Okay. And the restriction is this thing doesn't, it just falls through with an error case and returns nil, and you got to deal with it. Doesn't do error messages. So we'll probably have to do a version that does error messages at some point, or once we get to parsers that that can fail, or that we care about the failure. In this case, we're just falling through and we don't care. All right. Make sure this change is good. I really should have checked in first. Okay. Add a WrapNew class that converts new style parser to something more like recursive descent. I think that's honest enough. All right, now I had something else flitted through my little head here. I don't know if I need this stuff now. If it's the only type like that, can I just say parser? Build. Remember parse. Oh, okay. Yeah, that's true. So parser here is a protocol, and this is a parser. If I just did it the other way, it doesn't know parser is a parser. It's just using it as a generic template name kind of thing. Okay, just run all those tests. Okay, all right. So I think we've got this end parser handler. We should be able to take this case out. That code should be dead. Okay. We never get there because if the new parser handled it, then we don't need it. Okay. Let's see if we can quickly deal with the rest of any of. Okay, so I think our any of, we do handle sets. Let's find it. Any of. We have a set of tokens, but simple statement. It really needs to do. I want to say more of like, let's put a map in. Let token to simple statement be of type token type, capital T, goes to statement, and it equals well, dot end, no, what was the token? Dot end. Dot end goes to statement dot end. Function did you function produces? No. Can I just do this? I'm not in a function. Let's pull that up top. Token to simple statement is token type maps to statement. Function. Oh. Wrong bracket. Okay. And what were our others? Dot remark goes to skip. I don't think I need this. Restore goes to dot restore. They're two different types, so that's legit. And dot stop goes to dot stop. Okay. Right. And let's find any simple statement. Okay, so I'm saying if you had a simple statement. Let's say simple statements. Token to simple statement of token. We return this. Okay. Will this work? Whoops. Convert token dot type. Okay, and then I can generalize this. I have end, remark, restore, and stop. Okay, to simple statement. Do those. See, we'll pick up speed a little bit at the end here. Okay, and then end, remark, restore, and stop. Okay, so if our new parser weren't handling it, we'd start getting unknown statements. Okay, I think that's a good place to stop. Okay, handle end, remark, restore, and stop as single statement cases with Combinator parser. Okay, so what have we got? We fixed a defect in the lexer. We fixed a defect in the combo parser, well, a limitation where it didn't publish an operator we thought it should. We let's see, we added a couple tests for those things. We added support for simple statements, little one-word statements that they go through a new style parser, and we have a very generic new style parser wrapper that lets recursive old style calls call a new style parser. And I think this will suffice if we don't have error handling. For the cases we don't have error handling, this will suffice. We'll probably have to define one that does error handling. We may change the interface on this one. I don't know. We'll see what works better. But I wish we were further, but that's actually a good thing to have. It lets a lot of parsers do their job. So cool. And we'll pick up there tomorrow, 10 a.m. Eastern Time to 12:30 p.m. or 3 to 5:30 p.m. UTC. Thanks for joining me today, and I hope I can catch you in the future. I think we're on track. I mean, things are working so far. It's good. All right. Take care. Bye-bye.